Let's determine order of the reaction. Or in this case, we only have one reactant, so we're going to determine the order with respect to reactant A. So here we have the rate law. Here we have the equation of the reaction. Here we have the rate law. Notice that the rate law is always written in terms of the reactant concentration, never the product. Our job is to determine X. That will be the order with respect to the concentration of A, or order in A. In order to determine X, we will substitute data into this equation. Here are our data in the table. So we're going to use rate 2. Rate from experiment 2 is 0.15. 0.015 molarity per second equals the rate constant, and the concentration of reactant A for experiment 2, that's what we're doing, rate 2, experiment 2 is 0.20, and we are going to determine X. We divide this by the rate 1, 0.015 molarity per second, equals K. We do all these experiments at the same temperature, and the concentration of A is 0.10, again to the X. We do all the experiments 1 through 3 at the same temperature because K is temperature dependent. K is the same, will be the same for all 3 experiments. So K will cancel here. You can see that 0.015 divided by 0.015 gives us 1. The K's cancel. 0.2 divided by 0.1 is 2 to the X. So X must be 0 because any number to the 0 power is 1. If you didn't recognize this, we could take the log of both sides. Log of 1 equals log of 2 to the X. Now we'll expand the log. Log of 1 equals X log of 2. Divide both sides by log 2. Log 1 divided by log 2 equals X. And we can keep this all in base 10, and you can knock this out on your calculator. Log of 1 is 0. We don't care what log 2 is because 0 divided by any number will be 0. So X equals 0. That means the order of reaction with the order in A, or the order of the reactant with respect to A is, order of reaction with respect to A is 0. So the rate law is rate equals K, concentration of A to the 0 power, because 0 is the order. And of course, A to the 0 is just 1. Right, this is just 1, so rate equals K. So for a 0 order reaction, notice, what do we notice? That the rate was independent of the concentration. Although the concentrations were changed, the rate did not change. And for a 0 order reaction, this is what the rate law looks like for a reaction where there's only one reactant. Now let's look at the next one, a first order reaction. How do we know it's first order? You can try setting this up and then stop the video, try to set it up and see if we have the same setups. I typically use I divide a higher number experiment by a lower number experiment just because then the math is a little bit easier. It doesn't matter if I use experiment 4 and 6 or 5 and 6 or 4 and 6. You can use whichever you like. I decided to pick experiments 6 and 5, so I substituted those values for the rate and for concentrations, and 0.06 divided by 0.03 gives us 2. The K's will cancel. 0.4 divided by 0.2 is 2. That's the Y. So Y has to equal 1. So that means this reaction is first order in B, and the rate law can be written simply. Notice that here I'm going to have parentheses. It's not required. I put parentheses once I substitute the concentrations, but square brackets mean concentration. So that's why I keep square brackets when I don't have a value, but round parentheses when we actually have a numerical value. So we've done zero order. We've done first order. Now let's take a look at second order. Before we proceed to second order, let's have a look at the data for first order. Notice that when as the rate doubles, the concentration doubles. So just to recap, for zero order, the rate was independent of the concentration. Rate was independent of concentration. The rate did not change when we changed the concentration. However, for first order, when we double the concentration, the rate is also doubled. So that's a classic first order behavior. Now we're on to second order. Let's set it up the same way. You can pick any two experiments. Why don't you go ahead and do it on your own and then check with my setup. Arbitrarily selected experiments 8 and 7. Dividing the rates, we get 4. The K's cancel because experiments 7, 8, and 9 were all done at the same temperature. 0.2 divided by 0.1. So Z equals 2. This reaction is second order in B. I have a typo here. Sorry about this typo. This should be C, and this is C, because our reactant is C. So the rate law is, notice we write C in square brackets, that means concentration, and this is our rate law. So for the rate law, we do not have to find the value for K. The rate law is always written in terms of the reactant, never product. The rate constant K for a given reaction is constant at a given temperature. 3 or more experiments must be conducted at the same temperature so that the K values will cancel in the calculation of order with respect to reactant. So experiments 1 through 3 were conducted at the same temperature, 4 through 6 at the same, and 7 through 9 were conducted at the same temperature. The rate law is determined experimentally. The order of the reaction does not relate to the coefficients of the balanced equation. And the rate law is different from the rate expression. Now let's take a look at determining the order of a reaction when we have more than one reactant. So here we have nitrogen dioxide reacting with carbon monoxide to produce product. Here's our rate law, not quite finished yet. It'll be finished when we determine the order with respect to X and Y. In order to set this up, we determine the order with respect to one reactant at a time. Let's first determine the order with respect to NO2. If you want to determine the order with respect to nitrogen dioxide, keep the concentration of the other reactant constant. So I'm going to initially use experiments 2 and 1. Experiments 2 and experiment 1. So I'm going to put in the rate and the concentrations and do my calculation. Please pause the video, set it up yourself, and see if we're getting the same thing. Dividing the rates, we get 4. The K's will cancel. 0.2 divided by 0.1 equals 2 to the X. And now you can see the reason for picking 2 experiments where the concentration of carbon monoxide was the same, because that will cancel out, meaning X equals 2. So now we know the order of reaction with respect to nitrogen dioxide is 2. And now we're going to calculate the order with respect to, we can also say that the reaction is second order in nitrogen dioxide. Now let's determine the order with respect to carbon monoxide. So we're going to determine Y. So which two experiments should we use? Well, we'd like to keep the concentration of nitrogen dioxide constant. That'll be the easiest thing so that they'll cancel. So how about we use experiments 2 and 3 because the concentration of nitrogen dioxide is the same. So let's set up that calculation. Math. 0.0083 divided by 0.0082 is essentially 1. The k's will cancel. 0.2 squared divided by 0.2 squared, that will cancel. We did that intentionally. We wanted it to cancel. That's why we selected those two experiments 3 and 2 so that the concentration of nitrogen dioxide would be the same. And 0.2 divided by 0.1 is 2 to the y, and that means y equals 0. So the reaction is 0 order with respect to carbon monoxide. The overall order of reaction is the sum of x and y. That means 2 plus 0, which equals 2. So the overall order of reaction with respect, the overall order with reaction is 2. And now we can determine the K. Once we determine the order for each reactant, we determine the K. But I can now write the rate law. So rate, because we know the order with respect to each reactant. So concentration of NO2, that was second order, and concentration of carbon monoxide was 0 order. Simply put, we would write this as nitrogen is rate equals K, concentration of nitrogen dioxide to the power of 2, meaning second order, since this right here goes to 1. So this is the final rate law. Notice that we do not have to calculate K to determine the rate law. We've determined the rate law, but sometimes we're also asked to determine the rate constant K. So we can, got a little typo here. We can determine the K by using any experiment here. It doesn't matter. So let's just use experiment 4. It's right here for experiment 4. We've got rate 0.00. Whoop, mistake there. Equals K. The concentration of nitrogen dioxide is 0.40. That's squared. Concentration of carbon monoxide, that's to the 0 power. So we've got 0.033 molarity per second equals K times 0.40 squared, because 0.1 to the 0 power equals 1. So now I'm in my calculator, I'm going to square this quantity, and then I'm going to key in 0.033 divided by second answer. We get K equals 0.20625. Now the units of K are critically important. This answer would be marked wrong without the units. So remember that this is molarity. So I want to show you how I calculate the units. I've got molarity per second, that's the rate. K we don't know. And 0.4 is molarity squared, which is molarity. So if I want to solve for K, I'm going to divide both sides by molarity squared. So that means molarity per second divided by molarity gives me K. And then this will cancel so that my units are reciprocal molarity, reciprocal seconds. Well, since you used your calculator, so I just want to show you what I'm doing in the calculator. I squared the 0.4, so that's 0.4, and I square it, and I press enter. I press enter after every operation, so I don't need to use parentheses and worry about order of operation errors. Then I type in 0.033 divided by second answer. So the blue key and then the minus key right here, see the answer? And that's how I get that value. So that's all for this video. See you in class.